right, continuity and one-sided limits. A function is continuous, uninterrupted at C if these three things apply. To prove something's continuous, we have to show all three of these things. One way to think about continuous is if you can draw the graph without lifting your pencil. So for example, this graph right here is not continuous. Even though I could draw it without lifting my pencil, the hole represents an opening, a gap, and technically we wouldn't be going across there. Or if I wanted to emphasize it even more, I could put a point up here. So that's not continuous. That's an example of something that's not continuous. All right, so we will come back to that example. So first of all, to be continuous, a function must be defined. To be continuous at C, the function must be defined at that value. It must exist. So hopefully that's pretty clear. The limit has to exist at C. And that means that the left side has to equal the right side as we approach C. And then the last thing is that these two things have to be equal to each other. The limit that we're approaching has to be the value of the function. Now that may not seem clear, but I'll show you how we use that in a little bit. All right, a discontinuity is removable if f can be made continuous by redefining the point at a single value. Okay, so first of all, is this function defined at C? Again, pause the video, answer the questions as much as possible. Anytime you can pause it and answer questions yourself and then check what you thought the answer was, you're going to learn a lot more that way. Okay, so the answer to this is no, it's not defined. There's no y value at C. Does the limit exist at C? Now, some students want to say no, but the answer is yes. From the left, we're coming up here, we're approaching this, whatever this y value is over here. And from the right, we're also approaching that same number. Both sides are approaching the same number, so yes, the limit exists. We don't have to exist at the point because for a limit we never get to that point anyway. Kind of like some of my stories, never getting to the point. So, removable, some of my stories, not all of them. Removable. It's removable if we could fix that one point, if we could fill it in, and so yes, we could do that here. If we could plug the hole, we would be fine. All right, is the function defined at C? Again, pause, answer. So, yes, there's a value at C right there. Does the limit exist at C? Okay, well, for the limit to exist, the limit as x approaches C from the left of the function has to equal the limit as x approaches C from the right of the function. That is not true. The left side is approaching this, the right side is approaching this, the left side is approaching that, the right side is approaching that. No, the limit does not exist. It's approaching two different numbers at C. Is it removable? Is it one single problem? No, there's a gap in between there. Okay, is this function defined at C? Pause, answer. So yes, it is. There's a dot up there. Does the limit exist? Yes, the limit does exist. The limit is actually this, not that, but it does exist. That's just to distract calculus students. Don't fall for that. That's a trap. Okay, let's put that on there. Trap. Don't go for that point. That's almost never going to be the answer. The only thing that would be the answer to is what is f of C? F of C is equal to that. But that's rarely going to be asked. So, is it removable? Yes. If we get rid of that and plug in a point here, yes, we could fix that. All right. Now, this is, when I highlight stuff, that means it's going to be on a test. So, I highlighted this up here. That needs to be something we're aware of for testing. Down here, this is so often on tests that I'm going to highlight the whole thing. well, not literally the whole bottom part of the page, but I'm going to highlight all of that to emphasize to you that you need to know how to do this. This is a very common AP question that we see. So, what is the limit of this function as x approaches 1 from the left? So, get on the function and move towards x equals 1 from the left side. Well, the y value is approaching 2. So that's 2. Okay? What is the limit of the function as x approaches 1 from the right? So we're on the right side, we're coming this way, we're going towards 2. That's also 2. Okay? What's the limit of the function as x approaches 1? Well, it is approaching 2 from both sides, so since those are equal, the limit is that number, 2. So we move over here, we look at a similar situation. What's the limit of the function is, again, pause and try to answer all three of these. Or at least pause and answer the first one and then check and then pause again. So as x approaches 1 from the left, so here's x is 1, all along here that's x equals 1. Okay, so as we approach 1 from the left, we're approaching 3. As we approach 1 from the right, we're approaching 1. Those numbers do not equal each other, and if we were doing a free response question, we would write the limit as x approaches 1 from the left of the function does not equal the limit as x approaches 1 from the right of the function. So that is does not exist. Does not exist. Okay? All right. Discuss the continuity of the function. There are three types of discontinuities: removable, jump, and infinite. And we've already looked at a removable and a jump, and so there probably is an infinite coming up soon. Excuse me. So this is a rational function. Rational functions often have asymptotes, so we can think about vertical asymptotes. So vertical asymptote is where we are dividing by 0. So this is an opposite factor. We could factor out a -1. That would actually be x minus 5. We don't have to do that. We're going to use it somewhere, I think, or we have used it in some other notes. But so our asymptote is our vertical asymptote is at x equals 5. So we can come over here, and we can put a vertical asymptote at 5. Horizontal asymptote. So horizontal asymptotes we can tell by thinking about what happens as x approaches positive infinity and negative infinity. We could also use the degree rule for this part. So we could say the degree of the denominator is more than the degree of the numerator, so this is going to approach 0. Now if you want to think about that numerically, put in infinity, put in a million, put in a billion. If you put in a billion, 5 minus a billion is negative 999,999,995. So 1 divided by that is going to be pretty tiny, pretty close to 0. So as we go to infinity, this is really close to 0. So 0 plus 2 is 2. So we have horizontal asymptote at y equals 2. All right. Now, that's probably good enough. So if you want to do a little t-chart, see what's happening here, I would focus on that asymptote of 5. So maybe try 4. So if you plug in 4, 5 minus 4 is 1. 1 divided by 1 is 1. 1 plus 2 is 3. If I'm going a little too fast, just pause the video. Okay, so another good number might be 6. So 6. 5 minus 6 is negative 1. 1 divided by negative 1 is negative 1. Negative 1 plus 2 is 1. So 4, 3 is up there. This is right here. Now we're going to approach the asymptote, which means this is going to go here, and this is going to go here to pass through that point. Now, it is possible to pass a horizontal asymptote, but those are kind of unusual equations. We don't see those very often, but it is possible. All right, and this goes up here. So this is called an infinite discontinuity because the gap between the arrow up here and the arrow down here is infinite. So that's an infinite discontinuity at x equals 5. All right, now as we move over here, when we have rational expressions, functions, we usually want to factor and cancel. So we want to factor this. That's going to be x and x. Now this is positive. That means these both have to have the same sign, which means what two factors of 6 add up to 5? So that's going to be 2 and 3. And that's over x minus 3. So when we have a factor that cancels, so you want to be careful there. You might have thought that there was a vertical asymptote at 3, but that's incorrect because this cancels. And when that cancels, that means we have a hole, or what we call in calculus, a removable discontinuity. Okay, so that is going to occur at 3. X cannot be equal to 3. Now, if you divide that out, basically what we're looking at is y equals x minus 2. So if we plug 3 in here, we get 3 minus 2 is 1. So our removable discontinuity is at 3, 1. So we could actually go over there and we could put an open circle there. We could put a hole in the graph. Now, the equation that we're trying to graph is y equals x minus 2. That's a line. The y-intercept is negative 2. The slope is 1. And that does pass along the line with our hole. Okay, so that is going to be right here. All right, and that's all we have for that. As we move on to the next functions down here, this is called the greatest integer function, that symbol right there. The slang term for that is the step function or the staircase function, and you will see why that is the case shortly. Starting off on our scale, I'm going to change the scale to 1, 2, 3 by halves, like this. So we could, this is in the calculator, but I don't think it's helpful, so I'm just going to graph it by hand. And the greatest integer function says, what is the greatest integer less than or equal to that number? So hopefully you remember your integers. That's negative 3, negative 2, negative 1, 0, 1, 2, 3, dot, dot, dot. So those are our integers. So let's just pick a number, 0. So what's the greatest integer less than or equal to 0? Well, it's going to be 0. Let's try another one, 1/2. What is the greatest integer less than or equal to 1/2? That's going to be 0. Try one more, 3/4. What's the, again, 0. Okay, let's skip to 1. Remember, pause whenever you can to try to, when you think you know some stuff. All right, so the greatest integer less than or equal to 1 is 1. All right, so if we look at what's happening here, we have 0, 0, so we plot that. We have 1/2, 0. We have 3/4, 0. all the way until we get up to 1. When we get up to 1, we have 1, 1. So that's up here. So this is going to go all the way up to 1, but it's never going to reach 1. It's going to be 0.99999, and then, so we're going to put a hole there. So that one's kind of hard to see, but now, if you think about it, now if you put in 1.5, that's going to be 1. So the same thing's going to happen. So we're going to get this, and then we're going to get this again. And then this side is going to come over here, and then this side is going to come over here, and there we go. And now you can see why it's called the staircase function, the step function. Okay, so here we have jump discontinuities at every integer of x. Okay. Now we have a piecewise defined function. I'm going to color code this. So I'm going to, for x less than 2, I'm going to use purple. So x less than 2 is right here. And then for x equals 2, I'm going to use blue, but that's just a single point there. And then for x greater than 2, I'm going to use pink. So that's going to be over here. So I have 3 sections of the graph, piecewise defined function. So the purple first, that is defined by the linear equation 2x minus 1. So the y-intercept is -1, the slope is 2, so the change in y is 2, the change in x is 1, but it's just less than 2, so it's an open circle right there, and we have that. Okay, now at 2 it's equal to 5, so at 2 it's equal to 5, that's right there. And then finally, after 2, it follows this equation, 1/2 x plus 2. So y-intercept is 2, the slope is 1. So that can't be graphed though, because that's on the purple section, and oops, I messed that up. Color-wise, that's supposed to be blue. Okay, that's supposed to be blue. And now I would be using the red, and this line has a y-intercept of 2, the slope is 1/2, so that is going through there. All right, so here, what kind of discontinuity is that? That's a removable discontinuity at, now, the removable discontinuity is down here at 2, 3. That's where we could fix it. That's how we could make it smooth. Okay, that's not the removable discontinuity. This is. All right. Test question. So this is more numerical analysis. So in numerical analysis, some students get confused by this, so I'll try to be as clear as possible, but what we want to do is we want to approach -5 from the right. So if you think about a number line, and you have a number line, and you have -5, and you're coming from the right, that would be getting really close to this. That would be -4.9. So if you plug in -4.9 plus 5, you would get the square root of 0.1. And now, the mistake that some students make is they think that we're actually plugging in -4.9. We're not. We're plugging in -4.999999. We're going to get really close to 5. So this is going to keep getting smaller and smaller, 0.0001. And when you take the square root of that, that's basically 0. We're just using -4.9 as one example to give us an idea of what's happening. In our mind, we have to continue to make that closer and closer to -5. So this represents, I already know what's happening with that, so I'm not going to keep putting 0, 0, 0, 1 in there to do that. All right, now if we try this one, to the left, coming from the left of 3. So the left of 3 on a number line is 2.9. So we have 2 times 2.9 minus 6. So that's going to be, what is that, 5.8? And I don't even really need to do that. As long as you realize that that's going to be less than 6, then you're going to know that's going to be negative. And the square root of a negative is imaginary, and so that's going to be does not exist. Dividing by 0 and the square root of negative numbers are the two things that we're being careful about. All right, to the left, we're approaching -1 from the left. So the left of -1 is -1.1. That's just one example. I could get closer if I wanted to. I could put -1.0001, but I don't need to do that. I can figure it out from here. So now you can see, basically, we have the same thing on the numerator and the denominator, but the absolute value of this is going to make it positive. And then this is going to be negative. So the same thing, that's going to be 1, but the signs are different, so that's going to be -1. All right? Okay. These questions here, so these two are very common questions on the AP exam, and the last one is a real AP question. So, in order for this function to be continuous, this piecewise defined function, the two ends, the two pieces, have to meet at the same point. So what we need is the limit of x squared minus a squared x as x approaches. What are they approaching? The boundary is 2. So as x approaches 2 from the left, and we need that to equal the limit as x approaches 2 from the right of 4 minus 2x squared. All right? So you just want to memorize. When you have a piecewise function, they're talking about continuity, you want to check. Now, actually, the very first thing, if we're trying to prove that that's continuous, is we want to show that f of 2 exists. So f of 2 is going to be 2 squared is 4. It's going to be -4. Okay. So let's come back here. So now, as we approach 2 from the left, basically we could just plug in 2 for x. So we're going to have 2 squared is 4, and then we're going to plug in 2 there. So, and a is well, it's a constant actually. So that's going to be it for that. And then over here we're going to plug in 2 also. So that's going to be 4 minus 2 times 4 times 2 squared. All right. So that's going to be 4 minus 2a squared equals 4 minus 8. So that's going to be -4. So now if we subtract 4 from both sides, we get -2a squared equals -8. Don't forget to pause. It's a little late on this one now, but x squared equals 4. Now, hopefully your honors geometry teacher emphasized to you that when you take the square root of a variable squared, you're going to get the absolute value of that. So the answer is actually plus or minus 2. All right. Now, this next question is very similar to that question, just has a third part. There's 3 pieces. So, here we have a boundary of -4 in between these two parts, and we have a boundary of 3 in between these two parts. So we're going to have the limit as x approaches negative 4 from the left of 5, and that needs to equal the limit as x approaches 4 from the right of the middle piece. Okay, so the 4 is the left and the middle. Well, this is just a horizontal line. This is just 5. So no matter what x is, this is always 5. So that's 5. Now if you plug 4 in here, you're going to get 8a. That's a negative 4, sorry. You get negative 8a x. Just kidding, we plugged in for that. Plus b. Alright, so that's about as far as we can go with that for now. So now we can look at the other two pieces, the middle piece and the right piece. So now what we need is the limit as x approaches 3 from the left of 2ax plus b, and we need that to equal the limit as x approaches 3 from the right of bx plus 5. So if we plug 3 in there, we're going to get 6a plus b. If we plug 3 in here, for x, we're going to get 3b plus 5. Okay. We need to simplify this a little bit, so I'm going to subtract 3b from both sides. So that's going to be 6a minus 2b equals 5. So now we have a system of equations. And if we look at these two equations, I can take this equation and multiply it by 2. And I'm going to flip the whole thing over. So that's going to be negative 16a plus 2b equals 10. So hopefully we all realize why I multiplied that by 2, because now I can use linear combination. I can add these two together. The b's are going to cancel. So that's going to be negative 10a equals 15. We're going to divide both sides by negative 10, and we're going to get a is negative 3/2. Then we can come back here and plug, we want to solve for b also. So that's going to be 5 equals negative 8 times negative 3/2 plus b. So negative times a negative is a positive. 8 over 2, instead of multiplying these first, I'm going to reduce the 8 and the 2 first. So 8 over 2 is 4, 4 times 3 is 12. Subtract 12 from both sides, b equals negative 7. So those are our answers for A and B. Okay? Now, this is an actual AP question. This was off the 2008 exam. It's number 77. There aren't 77 multiple choice. They skip some in between the calculator and the non-calculator section. So, that other example I did was very similar to this with the graph and asking you questions about it. So what's the limit of this function as x approaches 2 from the left? This is a great place. You should be able to pause and do this based on the example I did earlier. At least pause the video, go back and look at the other example with the graphs where I highlighted the whole thing and see if you can answer this question. Very important. If you can't answer this question right now, you need to be a little more careful when you take your notes about what you're trying to do. So, the limit of this function as x approaches 2 from the left. So, as we approach 2 from the left, we're approaching this up here. Okay? So, does that exist? That's a left-sided limit. A left-sided limit, it's just, that's fine. It's approaching this. So, yes, that's fine. Okay? The limit of the function as x approaches 2 from the right. Does that exist? As we approach from the right side, This is approaching something. Now, up here, so that's yes. Now up here, you might be saying, well, that's not approaching something. There's an open circle there. That doesn't matter. Existence at the point does not matter because we're still approaching this y value right here. Remember, for a limit, you never get to that point. You get really, really, really close to it. And you get so close to it, we just say, yeah, you're there. We might as well say you're there. So those two are good. Now, the overall limit, for the overall limit to exist, we have to be approaching the same number from both sides, and we're not. These two numbers would not be equal. This would be up here, this is down here. They don't join together. So that one is not. That one does not exist. Okay, we don't know what these are because this graph isn't labeled. So 1 and 2 are good, and that concludes these notes. Good job. Ask questions if you have any.